Causal discovery in linear models with unobserved variables and measurement error is a challenging task, as ignoring either of these challenges can lead to detecting spurious causal links among variables of interest. This paper studies the problem of causal discovery in systems where both unobserved common causes and measurement error can be present simultaneously. The authors consider linear models that include four types of variables: directly observed variables, variables not directly observed but measured with error, the corresponding measurements, and variables that are neither observed nor measured. The majority of previous work on causal discovery assumes that there are no unobserved variables and that variables are measured without error, leading to identification of the underlying structure up to Markov equivalence class in general. However, in real-world settings, unobserved common causes and measurement error are often present, necessitating approaches that can deal with these challenges. The authors characterize the extent of identifiability of the linear latent variable structural equation model with measurement error, linear LV-SEM, under separability condition, together with two versions of faithfulness assumptions. They propose a notion of observational equivalence and provide a graphical characterization of the models that are equivalent. A recovery algorithm is presented that can return models equivalent to the ground truth. The authors note that the challenge of measurement error is essentially a special case of the unobserved variable challenge, but with special properties that can be leveraged to improve identification power. They study the identifiability of linear LV-SEM-ME under two faithfulness assumptions: the conventional faithfulness assumption, which prevents existence of zero total causal effects of a variable on its descendants, and the LV-SEM-ME faithfulness assumption, which prevents additional parameter cancellation or proportionality among specific edges. Both assumptions are mild and their violations are zero probability events. Under the conventional faithfulness assumption, the model can be identified up to an equivalence class characterized by an ordered grouping of the variables, which the authors call ancestral ordered grouping, AOG. The authors' approach allows for the coexistence of the challenges of unobserved common causes and measurement error, while leveraging the properties of the measurement variables to improve identification. The paper discusses the problem of identifying a linear latent variable structural equation model with measurement error, LV-SEM-ME, from observational data. This model is characterized by two sets of variables, V and X, where V can be arranged in a causal order and each variable in V is generated as a linear combination of its direct parents plus an exogenous noise term. The variables in V are further partitioned into three sets: Y, observed variables; Z, measured variables; and H, unobserved variables. Each variable in X is a noisy measurement of one corresponding variable in Z plus an exogenous noise term, known as measurement error. The authors introduced two restrictions on the model for the sake of model identifiability based on observational data. Firstly, they assume that the exogenous noise term for any M-leaf variable, a measured variable that has no other children, is not distinguishable from its measurement error. Secondly, they assume that variables in H are all root variables, have no direct parents, and confounders, have at least two children. The matrix form of the canonical LV-SEM-ME is provided, which includes equations for unobserved variables, observed variables, and measurements. The authors also define the causal diagram of a linear LV-SEM-ME as a directed graph where nodes represent all variables in V union X, and there is a directed edge from W1 to W2 if and only if W1 element of PA, W2. An example of a causal diagram is given, including unobserved variable H, observed variable Y3, measured variables Z1 and Z2, and their corresponding measurements X1 and X2. The paper aims to provide a recovery algorithm that could return all models in the AOG and DOG equivalence classes, where AOG stands for all other graphs, and DOG stands for direct ordered grouping. The authors also discuss the extent of identifiability under two versions of faithfulness assumptions and provide preliminary results that were presented in a previous work. In this research paper, the authors explore the problem of identifying linear latent variable structural equation models with measurement errors, LV-SEM-ME, using observational data. The LV-SEM-ME model combines both unobserved variables and measured variables, which presents a unique challenge in terms of identification analysis. The authors first considered two special submodels: the linear structural equation model with measurement errors, SEMME, and the linear latent variable structural equation model, LVSEM. They then extend their analysis to the general form of LVSEMME, which includes both unobserved variables and measured variables. To achieve identification, the authors proposed two assumptions: the separability assumption and the faithfulness assumption. The separability assumption states that the mixing matrix, which transforms independent exogenous noise terms to observed variables, can be recovered from observations of x, y, up to permutation and scaling of its columns. The faithfulness assumption is a stronger assumption that ensures the model is identifiable. The authors provide an example of an LVSEMME model and illustrate how to derive the mixing matrix using the provided equations. They also discuss the implications of their proposed assumptions on the identification of the model. In conclusion, this paper presents a comprehensive analysis of the identification problem for linear latent variable structural equation models with measurement errors. The authors provide a detailed explanation of the assumptions required for identification and demonstrate their approach using an example model. This research contributes to the ongoing efforts in understanding the complexities of structural equation modeling and its applications in various fields. Here is a combined summary of pages 7 and 8 of the research paper. The authors discuss the separability assumption in linear LVSEMME, latent variable structural equation model with measurement errors, which states that the independent exogenous noise terms can be separated, allowing the mixing matrix to be recovered up to permutation and scaling of its columns. This assumption holds in settings where all exogenous noises are non-Gaussian or when the noise terms are piecewise constant functionals satisfying certain conditions. However, it is violated when all exogenous noise terms have Gaussian distributions. The authors also introduce the faithfulness assumption, which comes in two versions: conventional faithfulness and LVSEMME faithfulness. Conventional faithfulness assumes that the total causal effect of any variable on its descendants is non-zero. LVSEMME faithfulness is a stronger assumption that requires the rank of a submatrix of the mixing matrix to be equal to the size of the minimal bottleneck from a set of variables J to a set of variables K. The intuition behind LVSEMME faithfulness is that the structure of the causal diagram implies proportionality in the corresponding entries of the mixing matrix, which may be enforced by the graph. This assumption prevents extra proportionality among the entries in the mixing matrix that are not enforced by the graph. The authors note that both faithfulness assumptions are violated with probability 0 if all model coefficients are drawn randomly and independently from continuous distributions. However, in practice, due to sample size limitations, an approximate cancellation may be perceived as an actual cancellation, making conventional faithfulness a preferred assumption. The authors then present a graphical characterization of equivalence under conventional faithfulness, called ancestral ordered grouping, AOG, equivalence. AOG is a partition of the variables into distinct sets, where each cogent variable is assigned to a distinct group, and M-leaf variables or unobserved variables are assigned to groups based on their parental relationships. The AOG equivalence class is a set of models with the same mixing matrix, up to permutation and scaling, and same ancestral ordered groups. Here is a combined summary of pages 9 and 10. In the context of structural equation models with measurement errors, SEMME, and latent variable structural equation models, LVSEM, the authors discuss the identifiability of these models up to their ancestral ordered group, AOG, equivalence class, and direct ordered grouping, DOG, equivalence class. For a SEMME, each ancestral ordered group has at most one cogent variable, and each observed cogent variable belongs to a separate group. The induced structure on each ancestral ordered group is a star graph. Similarly, for an LVSEM, if a group has more than one variable, then there must be exactly one cogent variable, and the rest of the variables are unobserved variables which are parents of this node. The authors show that by fixing the center of the ancestral ordered groups for SEMME, and fixing the exogenous noise term of the center of the ancestral ordered groups as well as the choice of scaling and permutation of the columns of B for LVSEM, leads to unique identification of the models. Moreover, the authors introduce the concept of direct ordered grouping, DOG, equivalence, which is a more refined partition compared to AOG. For a given edge from a measured cogent variable to an M-leaf variable or from an unobserved variable to a cogent variable, certain conditions must be satisfied for identifiability. The DOG of a linear SEMME or LVSEM is a partition of the variables into distinct sets, where each cogent variable is assigned to a distinct group, and M-leaf variables or unobserved variables are assigned to the same ordered group as their parents or children if certain conditions are satisfied. The authors prove that models in the same DOG equivalence class have the same edges across the groups, and the induced structure on each direct ordered group is a star graph. They also show that models in the same DOG equivalence class of a SEMME have the same in-labeled graph structure, and models in the same DOG equivalence class of an LVSEM have the same graph structure. The authors conclude that the DOG equivalence class provides a more distinctive characterization of the causal relations among the variables compared to the AOG equivalence class, and that the trade-off between assumptions 2 and 3 lies in the ease of incorporation in practice versus the level of faithfulness required. In the context of linear latent variable structural equation models with measurement error, LVSEMME, this paper presents an approach to identify the model up to its AOG or DOG equivalence class. The key idea is to leverage the information about which variables are measured and which ones are directly observed. This leads to smaller equivalence classes and hence more identification power. The authors introduce the concept of minimality, which asserts that the ground truth model has fewer unobserved variables than any other models that have the same mixing matrix and observability indicator. They show that this assumption has a graphical characterization, similar to the condition in the definition of AOG. The paper then presents the main identification result for the LVSEMME model, providing results under assumptions 1 and 3 to emphasize the trade-off between the strength of the assumption and the resulting extent of identifiability. The authors define the AOG and DOG of an LVSEMME, and show that models in the same AOG and DOG equivalence classes are consistent with different sets of causal orders among the groups. The paper also presents recovery algorithms for the introduced LVSEMME model. The AOG recovery algorithm returns the AOG of the underlying model, and it is used in both AOG equivalence class and DOG equivalence class recovery algorithms. The authors show how to recover all models in the AOG and DOG equivalence classes based on the recovered AOG. Overall, this paper provides a comprehensive framework for identifying and recovering linear latent variable structural equation models with measurement error, leveraging the information about measured and observed variables, and introducing the concept of minimality to enhance identification power. This section of the research paper discusses two algorithms for recovering the ancestral ordered group, AOG, and the model parameters in the AOG and DOG equivalence class. The first algorithm, algorithm 1, is designed to identify the AOG from the mixing matrix W** operator. It iteratively selects rows and columns with the fewest number of non-zero entries, assigns them to separate groups based on their support, and checks whether any row corresponds to a cogent variable. The algorithm continues until all variables and noises are assigned to ordered groups. The second algorithm, algorithm 2, aims to recover the models in the AOG and DOG equivalence class. It first recovers the AOG using algorithm 1, then enumerates all possible choices of centers and noises for each group. For groups with only M-leaf variables or unobserved variables, there is only one choice. For groups including cogent variables, the algorithm considers all possible selections of centers and noises, calculates the model parameters B, C, D based on W** operator and the selected row and col, and thus obtains all models in the AOG equivalence class. Both algorithms are based on the mixing matrix W** operator, which can be recovered from observational data using methods such as overcomplete ICA when the exogenous noises are assumed to be non-Gaussian. The algorithms have a computational complexity of O, PCMN, and a space complexity of O, Mn, where M and N are the dimensions of the mixing matrix W** operator. Here is a combined summary of pages 15 and 16 of the research paper. The authors present two algorithms for recovering the AOG and DOG equivalence classes of a linear latent variable structural equation model with measurement error. LVSEMME. Algorithm 1, the AOG recovery algorithm, takes as input the recovered mixing matrix W** operator and observability indicators of the variables. It iteratively selects rows and columns of W** operator with the fewest non-zero entries, partitions the variables and noise terms into separate groups, and assigns them to the sets Unobserved, sequogent, and CMleaf. The algorithm outputs these sets, which are used to recover the AOG equivalence class. Proposition 6 is leveraged to recover models in the DOG equivalence class, which is defined as the set of models with the fewest edges. The authors show that any model that belongs to the same AOG equivalence class but does not belong to the same DOG equivalence class has strictly more edges than any member in the DOG equivalence class. Algorithm 2 recovers all models in the AOG and DOG equivalence classes. It takes as input the recovered mixing matrix W** operator and observability indicators of the variables. The algorithm iterates over all possible selections of centers and noises in the group sequogent, calculates the matrices B, C, and D, and adds the resulting model to the set MAOG. The set MDOG is defined as the set of models in MAOG with the fewest total number of non-zero entries in B, C, and D. The computational complexity of recovering the AOG and DOG equivalence classes is O, M rho M call PCMN, time complexity, and O, Mn, space complexity. The authors conclude that their methodology can learn the model up to the AOG and DOG equivalence classes under certain assumptions, but note that the accuracy of the provided estimate of the mixing matrix and the linearity assumption are limitations that require further research. This section of the research paper presents a comprehensive review of various studies and methodologies related to linear non-Gaussian causal models, particularly focusing on the identification and estimation of these models in the presence of latent variables and measurement error. The authors discuss several key concepts, such as the linear non-Gaussian acyclic model, LINGM, which is a widely used framework for causal discovery. The paper highlights the importance of considering latent variables and measurement error in causal modeling, as these factors can significantly impact the accuracy of inferred causal relationships. It also reviews different approaches for dealing with these challenges, including the use of anchored discrete factor analysis, Halpern et al. 2015, and the application of greedy search algorithms, Chickering, 2002. The authors emphasize the role of structural identifiability in determining whether a given model can be uniquely identified from observational data. They discuss various conditions under which linear non-Gaussian models are identifiable, including the presence of non-Gaussianity and heterogeneity in the data. Adams et al. 2021. Xie et al. 2020. Furthermore, the paper covers recent advances in estimating causal effects using linear non-Gaussian models with hidden variables, Hoyer et al. 2008, and the development of new algorithms for learning these models in the presence of latent variables, Salakalibar et al. 2020. In addition, the authors discuss the problem of causal clustering for one-factor measurement models, Cummerfield and Ramsey, 2016, and the estimation of causal effects in the presence of measurement error, Saeed et al., 2020. They also provide an overview of different techniques for learning linear non-Gaussian causal models, such as the direct method, Shimizu et al., 2011, and the use of independent noise conditions, Xie et al., 2020. Overall, this section provides a detailed review of the current state of the art in linear non-Gaussian causal modeling, highlighting both the challenges and opportunities in this field. It serves as a valuable resource for researchers working on causal inference and machine learning. The proof of Proposition 2 is presented in two parts: sufficiency and necessity. The sufficiency part demonstrates that if an unobserved variable high in the ground truth model M has an M-leaf child that satisfies the condition described in Proposition 2, then M is not minimal. This is achieved by constructing an alternative model M that includes all variables in M except for high, and showing that M has the same mixing matrix and satisfies assumption 1. The structural equations for the variables in M are derived, and it is demonstrated that the alternative model is acyclic and satisfies conventional faithfulness. The necessity part of the proof shows that if M is not minimal, then there exists an alternative model M, with fewer unobserved variables that has the same mixing matrix and satisfies conventional faithfulness. The proof involves partitioning the cogent and M-leaf variables in M and M into groups based on their row support in the mixing matrix. It is shown that there exists a group G in M that contains only M-leaf variables in M, and one of the variables in G is a measured cogent variable in M. The column corresponding to the exogenous noise term of G in the mixing matrix is shown to correspond to a latent confounder in M, denoted as high. The condition in proposition 2 is then shown to be satisfied on M. The proof also involves enumerating all models in the ancestral ordered group, AOG, and directed ordered group, DOG, equivalence classes by different choices of centers. It is shown that an LV-SEMME can be uniquely deduced given the mixing matrix W of the LV-SEM and a choice of the centers, and their corresponding exogenous noises, in each group. The structural equations of the variables in the alternative model M are derived, and it is demonstrated that M and M have the same mixing matrix and the same ancestral ordered or directed ordered grouping of the variables. Equations 5, 8 describe the structural equations for the variables in M and demonstrate how the alternative model M is constructed. The equations show that the structural equations for the variables in M can be derived from the structural equations for the variables in M, and that the alternative model is acyclic and satisfies conventional faithfulness. The paper discusses the structural equations of variables in a model M and its modified version M, focusing on the differences between the two. In model M, the center of a group is denoted as V with exogenous noise NVI, while in M, the center and corresponding exogenous noise are ZJ and NHL, respectively. The structural equations for V, ZJ, and other children of V and HL are provided, showing how they differ between M and M. The changes in parent-child relationships among variables in M compared to M can be summarized as follows. For V, it becomes an M-leaf node in M, with its parents being the parents of ZJ in M excluding V itself, plus ZJ. For ZJ, it becomes the new center, with its parents being the parents of ZJ in M excluding V, plus the parents of V in M. For any child Vk of V in M, other than ZJ, the new parent set in M replaces V by ZJ and includes additional variables that are the parents of ZJ in M. For any child VKL of HL in M, other than V, the new parent set in M adds the new center ZJ and all parents of ZJ in M. The paper also discusses the proof of the identification result under conventional faithfulness, specifically showing that the extent of identifiability of an LV-SEMME under conventional faithfulness is the AOG equivalence class. This involves proving that for the ground truth model M, any other model M, in the AOG equivalence class of M, and any model M, that has the same mixing matrix but does not belong to the AOG equivalence class of M. 1. M satisfies conventional faithfulness. 1. M is consistent with any causal order among the ancestral ordered groups that is consistent with M. And 1. M violates conventional faithfulness. Here is a combined summary of pages 23 and 24 of the research paper. The authors prove that for each cogent variable V, the ancestral ordered group of V includes its M-leaf child ZJ if V is measured and all other parents of ZJ are also ancestors of V, and unobserved parent H if all other children of H are also descendants of V. They prove by contradiction that if Vis an ancestor of V, in M, the total causal effect from V to V is 0, and the added edges in M introduce additional ancestors to V. The authors then define sup G as the row support of variables in G in W if G includes any observed or measured variables, and sup Yang as the column support of the exogenous noises of the variables in G in W if G includes any cogent or unobserved variables. They prove that for two different ancestral ordered groups GI and GJ, the following three conditions are equivalent. There exists a causal path from one variable in the group of GI to one variable in the group of GJ. Sup GI, subset of sup GJ, and sup ngj, subset of sup, ngi. The authors then prove that given M, a causal order among the groups is consistent with the causal order among the variables if and only if the set relations in the mixing matrix hold. Since M and M have the same mixing matrix and satisfy assumption 2, they are consistent with the same set of causal order among the groups. The authors also prove that if M does not belong to the AOG equivalence class of M, then M is not minimal. They consider the number of cogent variables in M, which is equal to the number of columns of W minus the number of unobserved variables. They show that M cannot have more cogent variables than M, and if M has fewer cogent variables than M, then M is not minimal. The authors then consider the cogent variables in M, and their position in the AOG of M. They denote these cogent variables as P and show that no two variables in P belong to the same ancestral ordered group of M. They also show that the exogenous noises of variables in P and M, denoted by NP, include the exogenous noise of at most one variable in each group. The paper discusses the identifiability of a linear, non-Gaussian, acyclic model, LVSEMME, under the assumption of LVSEMME faithfulness. The authors aim to show that the extent of identifiability of an LVSEMME under LVSEMME faithfulness is the dog equivalence class. To achieve this, they provide two parts of the proof. First, they demonstrate that for the ground truth model M, any other model M, in the dog equivalence class does not add extra edges compared to M, does not remove any edges compared to M, and satisfies LVSEMME faithfulness. This means that M cannot be distinguished from M. Second, they show that any other model M, that is in the AOG equivalence class of M but not the dog equivalence class, adds at least one extra edge compared to M, does not remove any edge compared to M, and violates LVSEMME faithfulness. This means that M can be distinguished from M. In the following sections, the authors provide detailed proofs for these claims, focusing on models within the same dog equivalence class and models outside the dog equivalence class but within the AOG equivalence class. They also discuss the implications of their findings for the study of LVSEMME models and their potential applications in various fields. The following summary bridges the content of pages 27 and 28 of the research paper, maintaining technical accuracy and depth. Assumption 3 is violated if an edge is cancelled in M. This is demonstrated through three cases: when V equals Zj, when V is unobserved, and when V does not equal Zj. In each case, the minimal bottleneck includes all variables in K and at least one extra variable, violating assumption 3a. The proof of 2c establishes that M has the same in-labeled graph structure as M. A mapping sigma M is constructed between variables in Z union Y, and another mapping sigma N is defined between variables in VC union H. These mappings demonstrate that for all variables V except V and Zj, the parent and ancestor sets in M and M are equivalent. The model parameters in M and M are related through an invertible mapping, as described in I.V. This mapping translates model parameters in M to model parameters in M, ensuring that if M satisfies assumption 3 with probability 1, then M also satisfies assumption 3 with probability 1. The proof of 2d shows that if M differs from M only in one choice of centers, then there will be at least one edge added to M. This is demonstrated by considering two cases: when Zj belongs to the same ancestral ordered group but not the same direct ordered group as V, and when HL belongs to the same ancestral ordered group but not the same direct ordered group as V. The proof of 2e establishes that if any edge is removed in M, then M violates assumption 3. This is demonstrated by showing that if all added edges are removed in M, then M violates assumption 3. The results imply that if the ground truth model satisfies assumption 3, then the probability that models in the dog equivalence class all satisfy assumption 3 is also 1. The analysis focuses on the implications of adding an edge to a model, specifically in the context of ancestral ordered groups, AOGs, and the relationships between variables. The discussion centers around the conditions under which a model, denoted as M, violates assumption 3, which pertains to the existence of a minimal bottleneck in the model. The authors consider various cases based on the type of variable, V, that the added edge connects to. These cases include V being a center node, ZJQ, a non-center node, VKQ, or a latent confounder, VLQ. For each case, the analysis involves defining sets J and K, which represent the variables in M that correspond to the exogenous noise of variables in the ancestral ordered group and the parents of V, respectively. The key finding is that in all cases, the addition of the edge leads to a violation of assumption 3. This is because the minimal bottleneck from J to K union, V, must include at least K plus 1 variables, which exceeds the rank of the matrix WJK union, V. This result holds regardless of whether V changes its position in the model or not. The authors also consider the scenario where the added edge is removed, and show that this leads to a violation of assumption 3 as well. This is demonstrated through a proof by contradiction, where it is assumed that all added edges are removed, and then shown that this leads to a contradiction. Finally, the authors discuss the implications of the added edge on the model M, which is obtained by adding the edge to M. They show that this added edge does not introduce any new ancestral relations, and that the proof of this claim is similar to the proof of 2b, but in a reversed manner. Overall, the analysis highlights the importance of considering the implications of adding edges to a model, particularly in the context of AOGs and the relationships between variables. The results demonstrate that the addition of an edge can lead to a violation of assumption 3, which has significant implications for the model's properties and behavior. The analysis focuses on the minimal bottleneck in the causal graph, specifically examining the relationships between variables in the sets V0, ANM, V, and VC. For a variable V in V0, union, ANM, V, intersection VC, the set J is defined as the variables in M, whose exogenous noise corresponds to the exogenous noise of a variable in V0, union, ANM, V, intersection VC. The set K is defined as PAM, Xi, intersection VC, where K subset equal ppm, Vj. The structural equation of V in M implies that rank, Wj union, V, equals, K. The minimal bottleneck must include at least one variable between V and F, V, for each V in K, as well as one variable on the path V0 right pointing arrow Zj right pointing arrow V in M. This implies that the size of the minimal bottleneck is at least K plus 1. This result is further generalized to the cases where V equals Vk and V equals Vkl, where Vk and Vkl are variables that do not change their position between M and M. In these cases, the sets J and K are redefined, and the analysis yields the same conclusion that the size of the minimal bottleneck is at least K plus 1. The equations and mathematical concepts presented in this analysis are crucial in understanding the relationships between the variables and the causal graph. The use of rank and matrix notation provides a precise and concise way to express these relationships. The definition of the sets J and K, as well as the function f, v, are essential in identifying the minimal bottleneck. The figures and tables are not provided in the given pages, so their contents cannot be summarized. However, the text suggests that the analysis is supported by the results presented in these figures and tables. The limitations of this analysis are not explicitly stated, but it can be inferred that the results are specific to the given causal graph and may not generalize to other graphs. Future work may involve exploring the applicability of these results to other causal graphs and investigating the implications of these findings for causal inference.